theorem. The limit, if the limit as x goes to infinity of f of x is L, and the limit as x goes to infinity of g of x is m, and m is not 0, then the limit as x goes to infinity of f of x over g of x is just L over m. Now, we just finished proving the limit of a product. So we're going to use that. We can reinvent. We can go and do the proof all over again for the fraction. But there's no point. Let's build on what we know. Well, the first thing in the proof that I want to show is that the limit as x goes to infinity of 1 over g of x is 1 over m. Well, this is equal to the limit as x goes to infinity of any old way of writing 1 over g of x. So one way of writing 1 over g of x is that way. So it's the limit of that. But we have a theorem that says we have a limit of a function to a power. You can find the limit of the function and then raise it to the power. But we know this limit. It was given to be m. So the limit we want is m to the negative 1 or 1 over m. Okay, armed with that, we have no problem doing this proof. The limit as x goes to infinity of f of x over g of x. Well, I want to write that as a product. This is equal to the limit as x goes to infinity of f of x times 1 over g of x. So now it's a product. F times 1 over g of x. We know that this is equal to the limit as x goes to infinity of f of x. This is the product rule at infinity times the limit as x goes to infinity of 1 over g of x. That is, it's the limit of this times the limit of that. Well, the first limit is L, and the second limit is 1 over m, and L times 1 over m is L over m. Theorem is proved. The main thing is that you had to establish that the limit of that fraction was 1 over m. It's a little bit different because here the numerator was 1 and here it's not. Keep watching these proofs.